Welcome to Lecture 1.6, Annihilators. Last time, we defined the dual of a vector space X to be the set X prime of linear scalar functions from X to K. We saw that if X is n-dimensional and is finite, then X is isomorphic to its dual, X prime, and both, of course, are isomorphic to K to the n. I encourage you to think about vectors in X as column vectors and linear scalar functions, or dual vectors as we call them, or covectors, as row vectors. Given a basis of X, we saw what the dual basis was, and we could think of each dual basis vector as the linear scalar function that just picks off the coefficient of xi. And an element in the double dual, x double prime, we could think of as an evaluation map. It takes a covector or a linear scalar function and it just plugs in x. So in other words, if we have a basis x1 up to xn, then an arbitrary element, x is a1x1 plus aixi plus anxn, then obviously this is a basis, then there's a dual basis, and each x, so L1 just picks off A1, Li just picks off AI, and obviously Ln just picks off An, and so forth. And then the double dual, as we know, is the set of functions from the dual to the field, and these functions can, for every vector x, the operation of plugging in x is such a linear function. And because these are all n-dimensional spaces, we know all of the functions are of this form. We introduced a scalar product notation, which was a bilinear function. So instead of writing L of x, which really biases us toward x being vectors and L being functions, we wrote it as L comma x. And this identifies the double dual with x. So here we could think of as x being the variables that we plug in and L being the fixed functions, or we can think of x being the fixed vectors and L being the input things that we vary and put in. And if we do that, then we can think of x as being a function of L, so that the vectors in x are canonically identified with the elements, the evaluation functions in the double dual. So I like this because it really it unbiases our thinking. And it also gave us some intuition that we don't always see. So we saw that AL comma x equals AL comma x equals L comma AX. This is something that is less clear. So you can see the bilinear structure here, and it's more hidden if we just think of it in here. What this really says in this notation on the right is that AL of x, so that's a linear function, equals a times L of x, which is equal to L of ax. So that's just linearity, but in this setting, it's bilinearity. In this lecture, we will study the annihilator of a subspace Y, which is the subspace that lives in the dual, consisting of all scalar functions that vanish or are zero on everything in Y. So that's called the annihilator. We will determine its dimension, which is called the codimension of Y. And we will also understand what the annihilator of the annihilator is. So we'll call this Y perp and this Y double perp. Let's get started. To repeat what I just said formally, let Y be a subspace of X. Then the set of linear functions that vanish on Y is its annihilator. And we write Y perp. So formally, this is the set of all L in the dual space, such that L of Y equals 0 for all Y in big Y. Our first result is that the dimension of Y plus the dimension of y perp is equal to the dimension of x. Now this should look a little bit familiar because we've seen theorems that are like this. Namely, we've seen that the dimension of y plus the dimension of x over y is equal to the dimension of x. So all we have to do is show that y perp has the same dimension as x over y. But now y perp lives in the dual space, and x mod y is a quotient of the regular vector space. But we know one more thing. We also know that the dimension of x mod y, the dimension of any finite dimensional space, is equal to the dimension of its dual. So x mod y prime. So we'll actually show that these two things have the same dimension, and we will do that by constructing an isomorphism from y perp to the dual of x mod y. Now that maybe seem a little bit weird, like, what is that going to look like? But let's go with it and see what happens. I think you'll see that it's more straightforward than you might expect. So let's write that down. So we'll construct an isomorphism. Let's call it phi from y perp to x mod y, the dual of x mod y. So let's think about how to define that. So y perp consists of all linear functions that vanish on y. So script L, I'll just call it L, is one of these guys. And where does that get sent to? So that has to get sent to some linear function on x mod y. So it's a function defined on x, or on equivalence classes of x. So remember, x bar is going to be of the set of all x plus y, where y is in y. So this is an equivalence class. And the reason why this is going to work is because any two vectors that are equivalent, so in x bar, differ by an element in y. And little l is going to vanish on y. So that's why this is going to end up being well defined. Now I haven't told you how to define it yet. So let's send it, I don't know what to call this. Let's call this big L. So the image of this is going to be some linear function, and I have to tell you what big L is. So where big L is a linear function, scalar function from x, y to k, and think about how this is defined. So it sends x bar to, what scalar should it send x bar to? Now there's not too many choices. So how about x, or how about L of x? So it's a little weird. It sends it to a function of a function. So little l gets sent to the map that sends an equivalence class to L of x. So let's draw a picture. It's always good to have a picture along here. So here's so think of y as the xy plane again, and L is some function that vanishes on y. So let's say that L is like the height function. So L takes the vector and just outputs the height. So now y perp is the set of all linear functions that vanish on everything in the xy plane. And I claim that there is now we haven't proven this, but you could, I claim that there's a one dimension worth of such functions. So if I take a vector here, x, y, z, this linear scalar function that I just made up takes the height, but you could have also taken the function that's 2 times the height, or 3 times the height, or negative times the height. And I claim that these are going to be all of the functions. So this function L, so I've defined a function, the height, on all vectors, and I claim that we can extend this function this function is well defined for everything on this equivalence class. So the height of this is equal to the height of that, and the height of this, etc. That's basically what we're doing. This is a function on vectors, and we're extending it to a function on equivalence classes. And I claim that this is well defined. Now let me clarify what I mean well-defined. We have two maps here. So the domain of this map is just a vector space. There's no equivalence classes here, no ambiguity. L, the definition of L involves an equivalence class and a choice for that equivalence class. So what I've got to show is that L is well-defined. And of course, if L isn't well-defined, this map is not going to work either, because this definition, if this L doesn't work, the map to an L doesn't work. So let's check that L is well-defined. So remember, that means that we have two equivalent vectors. So we have an x here. Suppose we have an x prime here. So let's say that x bar equals x prime bar, or which is the same thing as saying, and equivalently, x is equivalent to y mod, x is equivalent to x bar, x prime mod y, which is the same as saying that x equals x prime plus little y for some little y and big Y. Okay, so now L of x equals, by definition, little l of x. That's what this, how this is defined. And this is equal to little l of x bar plus y, which is little l of x bar plus little l of y. Of course, that is 0. So this is little l of x bar, and that is by definition big L of, I got to be careful, big L of x prime bar. And you know what? I forgot that over here. It's not big L of x, it's big L of x bar. So you got to be careful with notation, so we don't make mistakes like this. Okay, so L is well defined. That is good. Now, what do we have left? We have this function here. We got to show that this is linear, that it's one-to-one, and it's onto. Now, it's almost trivial that this thing is linear. It's one of those things that writing it down is almost makes it more confusing than it has to be. Let me at least try. So phi is linear. So phi of, so let's take a linear combination of things that vanish on y. So phi of, say, L or AL plus BM. And this is some linear function on the duals, or on the quotient space, that maps equivalence classes to the evaluation of this. So this, I don't know how to write this, but this sends, I'll just say, sends it to F, where F of x bar equals AL plus BM of x, which is AL of x plus BM of x. And now I think it's just easier to say that A phi of, look at A phi of L plus B phi of M. And notice that what we're going to get is A times the function, I don't know how to do this notationally, that sends x bar to L of x plus B times this function, which, you know, we have notations with this. A times, yeah, sure, A times L plus B times M. And so A times L is this function and B times M is this. Okay, so as I said, I think the notation is worse than the actual intuition itself. So now I am out of room. Let me show that it's one-to-one and onto on a new slide, though I think really both of these are almost trivial enough that we can omit them. Finally, we just have to check one-to-one and onto. So let's check one-to-one. I always like to draw the picture because it's easy to mess up. That if you have two, so if you have an L and an m that get mapped to the same place, then they have to be the same. So in other words, let's say that phi of L equals phi of m. So what that means is, so then this function L that maps x bar to L of x is the same as m. So m maps x bar to m of x. So in other words, L and m are the same linear function. And so I think that's clear enough that therefore L and m have to be the same. Now I understand that if you're not convinced, let me leave the rest as an exercise. So I guess it's not a completely convincing argument, but it's also not hard either. So if you take a basis, so to show why these have to be the same, start with a basis for y. So take a basis y1 up to yk for y and extend to a basis for y1 up to yk, x k plus 1 up to xn of the whole space. And then think about what L and m are. So L and m say that L of yi equals m of yi equals 0 on this basis. And then a basis for the quotient space, remember, from an earlier lecture was xk plus 1, xn, and L and m have to agree on these because they're the same. And therefore they have, or I should say, the big L and big M agree on these, and therefore little l and little m have to agree on these vectors. So L and M, together you can argue that L and m have to agree on the entire basis, and therefore they are the same. But again, that's more work than I think it really has to be. I think it's fine to say that this it follows that L and m are equal from here. Finally, why is this thing onto? Well, if we take any big L in here, so any linear function from here, from x mod y to k, defines a linear function from x to k. So let me write that down. Any linear function L from x mod y to k defines a linear function little l from x to k, and how you define that is L of x equals big L of x bar. So again, if I've defined a function up here like the height of this equivalence class, then it is easy to extend that to the individual vectors, the height, or that function of this x or x prime, etc. And this is exactly how you do it. And I'll let you verify if you want that this is well defined. It's basically what we did in the previous slide. Okay, so we have a function that is one-to-one and onto and linear. This is an isomorphism. Therefore, the dimension of these two spaces are the same. And since we know that dimension of y plus the dimension of x mod y, or x mod y prime, equals the dimension of x, this theorem follows. Motivated by the previous theorem, we will define the dimension of y perp to be the codimension of y in x. And we'll write that co-dim y. I don't know how to say it. Just say codimension. Now, one thing you may be noticing or wondering is, well, this should remind you of the orthogonal complement, assuming you've seen that before. And indeed, if you have a subspace y, then, well, the annihilator, y perp, is a set of linear functions, which, think of y as column vectors and yperp as row vectors. And so, that row vector, thinking of it as a function of a column vector being 0, just means that those vectors are orthogonal. So if you identify row vectors with actual so you can identify x prime with x, these are isomorphic, by basically declaring these row vectors to be column vectors, then what that does is it literally takes these row vectors to column vectors that are orthogonal to the subspace Y. So that's the motivation for this, and later in this class we will identify the dual of a space with itself when we look at inner product spaces, and this will, and the vectors that this gets mapped to will be the orthogonal complement. If you haven't seen orthogonal complement, don't worry about it. We're doing it later. Basically, it's the subspace that is perpendicular to Y. A simpler way to state theorem 1.10 is that for any subspace, its dimension plus codimension is the dimension of the full space. Now, since the annihilator is a subspace of the dual, the annihilator of the annihilator, which we will write as Y double perp, is a subspace of the double dual. The next result says that if X is finite dimensional and we canonically identify the double dual with X itself as we usually do, then Y double perp is just the subspace Y itself. And if you're thinking about things as orthogonal complements, this makes sense. The complement of the complement is the space itself. So to prove this, I'm actually going to rewrite this back as the dimension. Well, before I do that, let's take the annihilator yperp and apply it to theorem 1.10. Now, theorem 1.10 said that the dimension of Y plus the dimension of yperp equals the dimension of X. And this is true for any subspace. So if we do this inside the dual for this subspace, then that says that the dimension of yperp plus the dimension of the annihilator of this, which is Y double perp, equals the dimension of X prime, which is the dimension of X. So in other words, we have these two things being equal, and we can cancel these, and we conclude that the dimension of Y and the dimension of Y double perp are the same. So both of these are sitting inside of X, and so all we have to do is just show that one of these is contained in the other. So let me write that down. Let me summarize what I did here. So by theorem 1.10, dimension of Y perp plus the dimension of Y double perp equals the dimension of X prime equals the dimension of X equals the dimension of Y plus the dimension of Y perp. Thus, the two things that I circled that are equal, thus the dimension of Y is the dimension of Y double perp. So it suffices. So it suffices to show either that show that one of these is contained in the other. So to do this, let's pick an element in Y, and let's consider any covector L. So what I claim is that for anything in Y, this is going to determine an evaluation map. And that evaluation map is going to annihilate or kill this L. So the evaluation map Y that sends L to L mod y is 0. So, i.e., L mod y is the 0 map. So Ly equals 0 for all L in y perp, by definition. So therefore, if I take anything in y, it is contained, it's the corresponding evaluation map, or is 0. In other words, it annihilates everything in y perp. So thus, y is contained in y double perp. So every vector in y annihilates everything in y perp. And that's it. We've shown one of these containments. So these two vector spaces, y and y double perp, have the same dimension, and one of them is contained in the other. We are done. Our definition of the annihilator was for a subspace, but we can similarly define the annihilator of an arbitrary subset S of X in the same way. So S perp is just a set of linear functions in the dual such that L of S equals 0 for everything in S. Recall that the smallest subspace containing S is the span, and there's two ways to define this. On the left is the set of all linear combinations of things in S. So you can think of this as building it from the ground up. And on the right is building it from the top down, the intersection of all subspaces that contain X. Remember that we went through this in detail in a previous lecture. So I encourage you, if you don't see why this is true, to go back and watch that. So we'll leave as an exercise that the annihilator of a subset is basically the annihilator of its span. And one helpful fact to prove that is also very simple, is that if S is contained in T, then the annihilator of T is contained in the annihilator of S. And that's easy to see with a picture for why this is true. So if S looks like this and T is bigger, then it's clear that it's harder to kill off things in T than things in S. In other words, if we have a linear function L that is in the annihilator of T, so L kills off everything in T, then it's clear that it kills off everything in S because S is a subset of T. So L is in S perp. So that's why this is true. I'll let you write this up into a formal proof if you want to. And then from here, it's fairly easy to show that the annihilator of S is just the annihilator of the span of S. Okay, that's the end of the series of lectures. In the next section, we will study linear maps abstractly using vector spaces, and we will still not introduce the concept of a matrix, though I still like to use things like row vectors and column vectors as visualization tools, like we do with long division. There's just ways for us to visualize n-tuples that are in ways that are convenient. And my goal is, in the next section, to completely and utterly convince you why studying linear maps abstractly is much better than doing it in terms of matrices, where we have pivot rows and free variables and upper triangular matrices and double subscripts. So by the end of that section, you will be absolutely convinced that we are doing things the right way, because I will give some applications to some things like polynomials and ODEs and PDEs that we would not have been able to do in a matrix setting. So stay with us.